Now you're working on a legacy code base and encounter a method that's 100 to 150 lines long. It works, but you need to understand it to add a feature. You read through it once, twice, three times, and you're still confused about what it's actually trying to do. Now, the horseshoe technique is a simple approach to untangle this kind of code. Translate it to plain English to understand its purpose, then rewrite it so the code clearly expresses that purpose. Today, I'll show you exactly how to apply this technique using a real example, which is a matrix style digital rain animation that started as messy code and was transformed into something else. Now, let's look at the original code. It's typical legacy code that works, but it's hard to understand. Now, let me walk you through what it's doing over here. So at the top, you see we have some constants and ANSI code for terminal control, a character set with numbers and symbols, and dimensions which are 80 wide by 25 tall. In the main method, we create a random object and an integer array called drops with 80 elements. We initialize each element to a random number between 0 and 24. These potentially represent where each column's raindrop starts vertically. Then we enter an infinite loop. First, we print ANSI codes to clear the screen and set green text. Next, we have nested loops. The outer loop goes through each row, 0 to 24. And for each row, the inner loop goes through each column, which is 0 to 79. For each position, we check if the current row matches that column's drop position. If yes, we usually add a random character, occasionally a space. If no, we mostly add spaces and occasionally a random character. Now, after building a complete row, we print it. After entering all the rows, we loop through the drops array again and remove each drop down by incrementing its position with wraparound, or occasionally reset it to a random position. Then we sleep for some time and repeat the whole thing. Now, the code works, but it's hard to see the structure. What's the purpose of each part? And that's what we're going to figure out. Let's first break the code into logical sections. We're looking for chunks that serve a single distinct purpose. Now, let me walk you through the code and show you how to spot these boundaries. Section 1 is the initialization part. Now, here we are creating an integer array with elements, that's 80 positions, one for each column. Then we loop through each position and assign a random number between 0 and height, which is 25. So if column 0 gets random value 12, column 1 gets 7, column 2 gets 19, we're setting up where each drop starts vertically on the screen. Now, this section kind of runs once before the animation loop begins. It's pure setup establishing the initial state. Notice that it doesn't depend on anything from the loop below, and the loop doesn't modify it during initialization. It's kind of self contained. Section 2 is the screen preparation. This kind of manages the terminal state where it's completely different from character selection or animation logic. Even though it's just one line, it has a distinct purpose, preparing the display for the next frame. Section 3 is the frame rendering. This entire block has just one job. It takes the current drop position and renders them as a visual frame. It reads state but does not change it. Section 4 is where we're doing character selection. Even though this is nested inside the rendering loop, it's doing something conceptually distinct, making visual decisions based on position and randomness. This logic is complex enough and important enough to deserve its own method. And step 5 is the animation update. This creates the animation by changing state. It's fundamentally different from rendering, which shows state. This modifies the drops array for the next iteration. The boundary is clear. After we finish rendering, we update positions. So the key insight here is we've identified 5 sections by looking for different purposes: initialization, display management, rendering, visual decisions, and animation. Each serves a distinct role to make the rain effect work. Now, step 2 is to translate it into plain English. For each section, we write what it does in business or functional terms, not in technical terms. So, section 1 sets up starting positions for raindrops in each column. Section 2 clears the screen and sets green text color for the animation frame. Section 3 renders one complete frame for the rain animation. Section 4 decides which characters appear at which position, bright for drop heads and faint for trails. This is the visual logic, bright characters at the drop positions and occasional faint characters everywhere for the trailing effect. And section 5 moves each drop down one row, occasionally resetting to create continuous rain. Notice how the plain English reveals what the code is actually doing, creating a falling rain animation with bright drop heads and faint trails. Step 3 is to extract responsibilities. Looking at our plain English descriptions, we can identify the core responsibilities. Initialization, which sets up the initial state, that's section 1. Display control manages the screen clearing and colors, that's section 2. Frame rendering for creating each frame of animation, that's section 3 plus section 4. And animation logic for moving the drops to create motion, that's section 5. These are four distinct responsibilities that should be separated into methods. The main loop orchestrates them, but each responsibility should be its own clear piece. Now, step 4 is to refactor. Now, we rewrite the code incrementally, extracting one method at a time. Each method name will come directly from a plain English description. So, the first refactoring is the extract initialization. The plain English for this was sets up starting position for raindrops. Now, if we walk through this extraction, we take the array creation and initialization loop and wrap it into a method. We pass in the random object since we need it for random values. We return the initialized array, right? Now, the main method after this would typically look like, the change where we are actually looking at drop positions and calling this method. Instead of those three lines doing array setup, we have one line that clearly states its purpose: create initial drop positions. The intent is now explicit. Now let's look at refactoring 2. This is to extract the screen clearing. It clears the screen and sets the green color to text. That's the plain English version. Now we take a single line that prints ANSI codes and wrap it into a method. The name clear screen and set color describes exactly what those ANSI code accomplishes. No parameters needed because the constants are accessible. This is a simple extraction, but it clarifies intent. Now, the main loop kind of becomes what you see on the screen. What's improved here is that instead of the system.out.println, which forces you to understand ANSI codes, we have clear screen and set color, which tells us exactly what's happening. The third step is to extract the character selection logic. This is the nested if else logic. We extract it first before we extract the row building. Now, the plain English version of this is it decides which character appears at each position. So we take the entire if else block that decides which character to show and make it a method. It needs four parameters: the current row and column we are entering, the drop positions array to check against, and the random object for the probability decisions. Now, the logic is the same, but it's now more clear. If we are at the drop positions, the row matches the drop position of the column. We return a random character most of the time, or a space occasionally. This creates bright leading edge on the drop with occasional gaps. If you're not at the drop position, we return a space most of the time or a random character occasionally. This creates a faint trail effect above and below the drop. The fourth refactoring which we do is to extract the row building. That is, we are trying to render one row of the main of the rain animation. This method builds one complete row of 80 characters, and we loop through each column and call our get character for position method to decide what character goes in that position. We append each character to the string builder and return the complete string. The method name build row string is descriptive. The implementation is now just a simple loop with a clear purpose for each iteration. Get the character for this position and append it. Now, the rendering section becomes a simple for loop. The complexity would be kind of hidden behind the well-named method which we have. The fifth refactoring which we need to do is to extract the drop position updates. The plain English version of this, if you remember, was moves each drop down, occasionally resetting. We take the loop that modifies drop positions and make it into a method. It needs a drop positions array which it modifies and the random object for decisions. For each column, we check a random value. With 95% probability, we advance the drop by one row. This creates variation. Not all drops move at the same pace and some are randomly restarted. Now finally, we look at the final refactored main method. It reads like a narrative. We create the random number generator. We create initial drop positions. Then we loop forever. We clear the screen and set color, render each row by building its string and printing it, update the drop positions for the next frame, and then sleep for a small period of time. Each line clearly states what it does. A developer reading this immediately understands the animation loop structure without needing to dive into implementation details. Now, step 5 is to go ahead and validate what we've done. We check that each method matches its plain English description. The create initial drop position sets up the starting position. Clear screen and set color clears the screen and sets the green color. Build row string renders one row. Get character for position decides which character appears. An update drop position moves the drops down, occasionally resetting. The refactored code does exactly what the original did, but now the purpose is clear from the method names. Now, when to use this? Now, use the horseshoe technique when you encounter roughly 100 to 150 line methods that work but are hard to understand. This technique is specifically for that mid-size complexity range. Now, if you've got method names that are vague, like process data or handle stuff, the translation to plain English reveals what they should be called. If you need to modify legacy code but don't really understand it, this technique builds understanding before you change anything. Now, the key insight here is that translating code to plain English forces you to think about purpose, not mechanics. Once you understand purpose, the right structure becomes obvious. This simple technique will save you hours when dealing with legacy code throughout your career.